When we're talking about functions, we usually think of a function in terms of what goes into the function and then what comes out of the function. When you plug something into the function, you get something out. You plug in a 2, you get out a 10. You plug in a 3, you get out a 15. It might depend on what the function is, and maybe you might get the same thing to come out from multiple different things plugging in. But generally, it's a relationship. That's what a function is. It's a relationship between a set of x's and a set of y's. And generally, we call those things the domain and range. The domain is the set of all possible input values. Everything that you're allowed to plug in is the domain. It's the x-coordinates of the points, of the graph, of the table, whatever. It's the x values. The range is what we call the outputs. It's the set of all possible output values for a function. So it's the y-coordinates. And generally, what you could think of this as is that we have some blob that represents the domain, and every individual point in that domain, every individual thing, every spot in that domain gets sent to some other set of numbers called the range. And so we have other dots in there. And then the function is the actual action of going from one spot to the next. So there to there, and there to there, and there to there, and maybe this one also goes to the same one here, and it's this point. That mapping is the fancy math word for it, but that process of going from the domain to the range, that's what the function is. So again, the domain is the x values, the range is the y values, x coordinates, y coordinates. Makes it really easy when you're looking at a set of ordered pairs or a set of or a table like this to identify what the domain and range are. You just look for the x's and you look for the y's. So this first set here, these little curly brackets here indicate that these are being grouped. That's called a set notation. You'll learn a little bit more about that later on. But what this is saying is that I have 4 points, 5, 2, negative 5, 4, 7, 9, and then the origin, 0, 0. So if I want to list the domain and range, it's just a matter of listing the x values, the x coordinates, and the y coordinates separately. And it's useful to do this in order. We have negative 5 would come first, and then 0, and then 5, and then 7. List them in numerical order. They don't have to be the same order for the domain and range either. You don't have to leave them in the same order that they're written, and these don't really need to match up in the same order. Like 0 comes first numerically before the 4, so when I go to the range, I'll just put them in order as well. 0, 2, 4, and 9. So there we go. Domain and range for that first example is there. For tables, it's even easier because we basically have it all written out right here. The domain, and they're also in order. The domain, then, is just negative 5, negative 4, negative 3, and negative 2. And the range is then, oops, got to use my right notation. It is important that you use the little curly bracket there to show that this isn't a point or anything like that. Or an interval, 7, 12, 17, 22. 22, not 23. 22. 22. There we go. For the third case, you might notice that something's a little bit different here. You'll see that as far as the domain goes, there's a 12, and then there's another 12. As far as x coordinates go. The first 12 has a 2 with it, the second 12 has a 4 with it. So this actually, you should remember from class, means that it's not a function, because there's 2 values for x, or the same value for x, it goes to 2 different values for y. If we actually made a graph out of this, it would fail the vertical line test. This is all stuff you should remember from class. But as far as listing the domain, it doesn't really change anything, with the exception of the fact that I'm not going to repeat it. If 12 is in the domain twice, then that means we don't write it twice. We only write each number as it appears uniquely. So I'm not going to do 2 12s. I'm just going to say 2 and 12. And then with my range, I have 2, 4, and 12. So the domain just has 2 numbers in it, but the range has 3. And that's fine. That's perfectly acceptable. For tables and lists of ordered pairs such as these, it's pretty straightforward how to get the domain and range. You just list them. For graphs, though, it's a little bit more tricky. For graphs, we have to look at the scale. So on your notes there, make a note of this, that on this circle, we go over 1, 2, 3, 4, 5, 6 to the right. I'm going to do this in red, actually. 1, 2, 3, 4, 5, 6 to the left. 1, 2, 3, 4, 5, 6 up. And then 1, 2, 3, 4, 5, 6 down. So this is positive 6 over here. This is negative 6 over here. That's positive 6 and negative 6. The graph, keep in mind, is the actual circle part. This is actually the graph of the function, of the relationship. And I want to describe the domain and range. Well, I clearly don't have any values to the left of negative 6. There's no part of the graph that's to the left of negative 6. There's no part of the graph that's to the right of positive 6. So I know that my domain is not going to be bigger than 6 and is not going to be less than 6. And as far as between negative 6 and 6, I just want to see what value of x has a y. So if I draw a vertical line through this value of x, does it connect with the graph somewhere? Yes, it does. In fact, the graph connects it in 2 places. This, again, we say it's not a function because of that. But because it crosses the graph, that means x equals negative 4 is a part of the domain. And in fact, every x between negative 6 and positive 6 connects to somewhere on that graph. So when we're looking at a graph, we look at just to see what values of x have a y, what values of y have an x. So for my domain, it's everything from negative 6 to 6. And I could write that one of 2 ways. I could either write in inequality notation, saying that negative 6 is less than or equal to x is less than or equal to 6, or I could use interval notation, if you remember that from the previous unit. Negative 6 to 6, with the brackets to show that I'm including those numbers. For the domain, we got that. For the range, it's exactly the same. I don't have any values for y less than negative 6. I don't have any values for y greater than 6. But I do have a value for x that corresponds to every value for y. You draw a horizontal line there. You draw a horizontal line there. Every value for y between negative 6 and 6 has a corresponding x value. So then for the range, I have negative 6 is less than or equal to y is less than or equal to 6. Make sure you use y here, because the range talks about y. Or just use interval notation, and it kind of doesn't really matter. And so we have that. For the domain and range for this circle, we have this situation. Now this is a circle. Circles are easy to understand. It's everything in there. The next graph, though, is a little bit more interesting, because we have a line. The important pieces are these arrowheads. What this is showing is that the line continues on forever in both directions. It continues forever this way, and it continues forever this way. Which means that there is no value for x, because it keeps going this way. There's no value for x that doesn't have a value for y to the left. And there's no value for x that doesn't have a value for y to the right. Every single possible x value has a corresponding y value. And in fact, the same thing is true for y. Every possible y value has a corresponding x value. We might have to go down quite some time in order to find the x value, to find that place where the graph crosses, but eventually it will. And so for this particular case, the domain and the range are both all real numbers. Every number, every possible value for x, and every possible value for y, both work. So we can break them up individually, and we say, well, it's all real numbers for the domain and all real numbers for the range. And you could either say all real numbers, or you can use that fancy notation for all real numbers. math symbol that always means all real numbers. The last example here is, you might remember, called a parabola. And we have these arrowheads again, which again means that it keeps going forever, up here and up here. Which means that as far as the x values are concerned, as far out as we go, we'll eventually find, and it might be way up at the top, off the top of the edge of the graph, we'll eventually find a y for that. So the domain is all real numbers. When you draw a graph, when you have these arrowheads, generally the assumption is that it's never going to come back down again. You won't draw these arrowheads unless it really is just going that way forever. So do keep in mind. Is the same thing for the range? Is the same thing true for the range? Does every possible y value have a corresponding x? And you should see that it doesn't. Down here, there's nothing down here. There's nothing down here for y. The graph doesn't go down that far. So if I wanted to get a value for x that has a y value of -9, I'm out of luck. There's nothing down there. The graph doesn't go down that far. So we only go down as far as 1, 2, 3, 4, 5, 6. So it goes down as far as -6, but then it keeps going up. It does the positive end of y. It does. There's y's all the way up to infinity on that end. So I could say that y is greater than or equal to -6, or I could say, using my my interval notation, that it starts at -6, it includes the -6, but then there's no upper boundary. It just keeps going on forever. So when you have a graph, look for arrowheads. The arrowheads will tell you if your graph, if your domain or range might be all real numbers. Otherwise, like with the circle, just look at how far to the left it goes, how far to the right, how far up, how far down, and that's your domain, and that's your range.